Good morning and welcome to Oxford and to L4DC. My name is Antonis Papachristodoulou. I'm one of the co-chairs of this year's L4DC, along with Kostas Margelos and Alessandro Abate. And on behalf of the organizing committee, I'd like to welcome you to this 6th annual conference on learning for dynamics and control. Thank you for joining us and coming all the way to Oxford from all over the world to take part in what I think is going to be one of the most exciting and stimulating conferences in this intersection. Indeed, L4DC is recognized as the flagship conference at the intersection of learning, dynamics, and control and optimization. And it's a unique pleasure to be organizing this conference in Oxford this year. And actually, the rate of growth we've seen over the past few years and from last year to this year would have meant that we wouldn't have been able to organize it in a couple of years now. I just hope that the weather would be a little bit better. Unfortunately, we can't predict that. And I would have hoped that by this time, weather would have improved, but at least the locals will have to be more patient to get a glimpse of summer, I guess, if any. Now, there are 300 people registered for L4DC. Many of you are young academics and researchers, but what was interesting to see was so many of you work in industry. Now, L4DC's goal is to foster and grow a community at this intersection of learning, dynamics, and control, ask meaningful questions with societal impact, and lay the foundations for the future of principled learning for dynamics and control. And this, I'm sure you all agree, is already happening. It was launched in 2019 at MIT, and this 6th version has seen 214 papers submitted and 39 accepted, so that's 65%. And that's an increase of almost 20% from last year. So I think this is going to be, we see an increasing growth over the next few years. So at this point, I'd like to thank the other members of the organizing committee. They've worked tirelessly over the past year for L4DC 2024. Mark as program chair, Simone for organizing the tutorials chair, Mariam, the awards chair, the local and global publicity chairs, Ian, and Konstantinos, as well as our web manager, Jack. But also, obviously, the steering committee for entrusting us the organization of this year's L4DC. I also want to thank the 41 or so international program committee members that solicited more than 600 reviews for the papers submitted, and I'm sure many of you reviewed those papers, so thank you. The proceedings are now online, available on PMLR. So we look forward for an exciting event over the next couple of days. So this is today's schedule. You'll see we have 3 plenary speakers, keynote speakers today, and 3 more tomorrow, and then 2 oral sessions today, 4 papers each, and 2 more tomorrow. That's 16 oral presentations. And then our interactive poster sessions, 2 today and 2 tomorrow, will feature another 223 papers outside in the mezzanine. So from today's schedule, I'd like to highlight the award ceremony later on today at 5:45 p.m. Here, as well as a banquet dinner at Reuben College. Reuben is a short walk from here, but starts at 7. If you have a ticket and you know, because there would be an orange sticker or a piece of paper in your registration pack, please use it. If you are not coming to the dinner, please hand the ticket back to registration or to someone that's looking to come, because obviously we want to accommodate as many people as possible. There's a small typo on the ticket. It says Wednesday, 16th of July. Actually, it's Tuesday, 16th. There's no dinner tomorrow. But there is an equally interesting schedule for tomorrow with 3 more plenary speakers and more poster sessions and more oral presentations. At this point, I also want to thank our sponsors, Siemens, Quanser, MathWorks, Curise, and RT. They've got booths outside. Please talk to them, as well as the University of Oxford for supporting us. Now, before I hand over to Kostas, we'll introduce the first speaker. I'd like to share with you some practical considerations for the next couple of days. So this is the map of the venue. We're in L1 over there. And as you'll see, the posters will be along the sides of these walls, and then these are shown here are the booths for the sponsors. There's fire exits. There's here at the back as well, and then you need to exit the building. Obviously, there's a fire. If you have any questions, please contact any of the volunteers. They're sitting around you. They wear Oxford blue T-shirts with big L4DC signs on them. Or anybody else that's local will be able to answer your questions. Well, thanks again for joining us. I really hope you enjoy the conference. I'd like now to hand over to Kostas, who will introduce our first speaker.
Okay, so good morning also from my side. My name is Kostas Margelos. I'm one of the other chairs of L4DC 2024, and I will also take my turn to welcome you to Oxford and our conference. I have the pleasure to be chairing today morning the first keynote presentation session. We are privileged to have 6 outstanding speakers. I can see already some of them in the audience. And they cover, I would say, all the focus areas of L4DC, namely control, optimization, learning, as well as applications of those in different domains. So shortly, I will introduce the first one from that list, but before I do so, I would like to share with you a short message, a short video from one of our sponsors, namely Siemens, and take also this opportunity to acknowledge their support to our conference.
Certain they will perform flawlessly in every situation. With Siemens Autonomous Vehicle Development Solutions, you can leverage a closed-loop verification and validation process to deliver safe autonomy and accelerate certification. Verify requirements, validate that they are being met, and reduce the risk of real-world failures by testing virtually against a growing database of critical scenarios. Evaluate systems across multiple levels of simulated environments, including software in the loop, hardware in the loop, driver in the loop, and vehicle in the loop. Before on-road testing begins, identify any gaps that require further evaluation, and feed optimizations back into designs to ensure full coverage of requirements. Deliver trustworthy autonomy faster with closed-loop verification and validation from Siemens Autonomous Vehicle Development.
Okay, thanks again to Siemens for their support to our conference. If you want to find more about their activities, the Siemens booth is just on the right as you exit the auditorium, so you can chat more with them. Let me now switch back to our keynote speakers. And I have the great pleasure to introduce the first of them, Professor Na Li, is known as Lina, widely in our community. Lina has been currently the chair of the Winnaker Chair of Electrical Engineering and Applied Maths at Harvard University. Before that, she had several postdoctoral appointments, including MIT, and she obtained her PhD degree from Caltech in 2013. She has made fundamental contributions across different domains closely related to L4DC, control, learning, optimization over networks, pretty much everything. And despite her very young age, she has managed to get several distinctions, awards, and recognitions of her research and teaching. This list is too big to exhaustively go through it, so I will just highlight some of those. They include the NSF Career Award, several Young Investigator Awards, and most notably the Donald P. Ekman Award in 2019 and the Manfred Thoma Medal last year in 2023. So today Lina will talk to us about representation-based learning and control for dynamical systems. We very much look forward to your talk, and many thanks again for accepting our invitation to deliver a keynote in our conference. Before I hand over to you, I just want to make a very quick logistic announcement about the keynotes. We want to time those around 45 minutes, pretty much to keep track of the rest of the conference because we have a busy day ahead of us. So towards the end of those 45 minutes, I will start waving my hands in the first row just to signal you that the session should be coming to an end, and allow also a few minutes for questions from the audience. Okay. Let's thank Lina for being here, and the stage is yours. You can connect, you can just change to visualizer.
Morning, everyone. Thank you for coming to my talk. It's my great pleasure to come to this kind of like home community to share our most recent work on learning and control. So I want to give a heads up is many slides are actually fresh news slides with the result we just got last week. And that being said, most work I'm going to present today is ongoing work. I'm looking for feedback and collaborations. So given the interest of time, I will just give a very quick motivation of the talk to this community. So in the past decade, we have seen many exciting news about AI and especially deep reinforcement learning. Like we see how computer can beat human players in the Go, in the video games, and how computer can train a robot on the computer simulator. Or deep reinforcement learning can be used to fine-tune the large language model, having the exciting product, the GPT. So for those in case, right, I know most people already know what RL is. Quick introduction of the RL. So the exciting thing of like why so many people, not just our own community, even including the science, biologists, they kind of look into the RL because it looks like very simple to use. So we have an agent in aqueous environment. So the environment will we have the sensors to observe the state of the environment. The agent will, based on the observation, taking action. So in our language, we call it policy. How the agent really improve the policy is through the observation of the state and also the rewards that return from the environment. And the goal is trying to maximize the long-term reward. As I said, why so many people from different community trying using the RL, either doing the theory or apply it, is because most work algorithm treat it as a black box. It just keep playing it. So now let's put on one question. Once we try to transfer the success of the AI from the simulator computer to our physical system, I'm glad we just saw a video about autonomous driving. It's a real physical system. So we will face so many different issues. I put in some examples. I've been working on power grid for a long time, and there's autonomous driving. There's no traffic signal here. I don't know where exactly this street comes from. This comes from the real videos. We want to make a robot that can help in our daily life. And the last project I will talk about a little bit is actually from a collaboration with a biologist. So we try to use the bioelectronic signal to grow a tissue outside human body. So all of them has a one common theme is there's a physical entity, which is in outside environment, not really controlled by us. So what's the difficulties? There are many challenges. I will just put in 4 challenges at the beginning. So first, let's talk about the data. The big success of those ChatGPT large language model is because of data and the computation power. First, let's look at the data amount, and now we dive into our own applications. Even though we say we have an Internet of Things, the IoT generating a lot of data, but I've been working with IoT company on the demand response. The first time we look into it, half data is missing, and the data quality is really bad. And what is noisy or missing data, or human actually manipulate the data. So that's the challenges we have. And for the biology experiment, even I can control things in the lab, but one experiment will take 60 days and super expensive. So first is the data challenges. We definitely still need to improve the data efficiency of the algorithm, not just treating it as a black box. Now, since we have the data challenges, now a lot of people say we're going to build a simulator based on whatever the previous data or the domain knowledge is. So this is, I think, for the people who work in robotics, always facing these challenges. I can tune things in the simulator or tune in the lab, and then put in my robotics into the real physical system. There's always a gap because, yes, the dynamics, no matter how fancy we're going to model it, is not capturing exactly every element in the system. So now the safety, this is robotics, and this is the power grid. This is a huge challenge when I was trying to work with power industry is they're always afraid of that going to happen. What if just have a big blackout? And like, what are you going to do? And now the last one, I will also mention, like, if you think about autonomous driving and the power grid, even for the biology project that we have been working with, is we actually had not just like one sensor, we always has a huge amount of sensor monitor different locations. So the sensor generating a huge amount of data, and they actually really space it out. So about computation, for those success I've been saying, if you look at the news, I was trying hard to find, like, for the ChatGPT, exactly what's really parameter I've been using, how many, and how many GPUs, how many data, how many energy I've been used. And now we're stepping off the smart cities, such as smart transportation. Can we actually, like, for individual entity, you're going to have in this kind of so many number of GPU behind it? This is not scalable. So putting off them, like, how are we going to do it? So today, I will focus on the representation, like diving into actually more concrete question, like we're going to use representation, system structure, domain knowledge, right? Whatever we have, plus the advantage of RL, to think, can we achieve better performance? So as I've been working on different applications, I will be here for today and tomorrow. If you're interested for the specific application, I'm happy to talk. We work on power grid, we have the house zero, we have like even working with the doctors to developing an ultrasound autonomous medical device, ultrasound. And the last one is about the biologic project I've been mentioning before. But I'm not going to talk about everything, so let's dive into the detail of today's talk. I'll focus on the representation and also will touch some of the system network structure. So what the problem I actually will go through for today's talk, I think almost everyone's familiar in this cloud. Like, this is kind of the problem we always like open nonlinear control textbook, we'll see a nonlinear control, optimal nonlinear control problem. We go through it. So also I'm kind of changing the notation more like reinforcement learning rather than call X, state, U as action. I'm using state as S, action as A to bridge the gap between the two communities. So we have state, and we have a control action, and this is the state dynamics. The F right now here, you can actually keep it general, like doesn't matter what the F is. The theoretical guarantee will definitely depend on the F, but not going to touch that much in details. So we have a stochastic process because no matter what kind of like environment we're going to do, they always stochastic, it's not really modeled by the F. So we have the noise, and this is the reward, negative cost, like assuming we actually have some goal we want to achieve. And we put in the discounting factor to making the talk, like the technical is smoother for the presentation. And the goal is to try to find feedback policy to optimize the long-term reward. So this problem is kind of like standard. I didn't change anything. So most of us probably took nonlinear control either 1 semester, 2 semesters, or multiple years. We learned so many different tools. And I don't know your frustration. Like for me, like I like the feedback linearization a lot. It can change the problem to be a linear problem. And then beyond that, then there's so many different methods for a particular problem. And I remember I took a 1 semester class on the sum of squares programming. It's very hard to scale up to a large scale system. And on different computer probably will give us the different solutions. That's 1 decade ago. And I know there's a lot of improvement recently also. So like putting all those challenges, I'm not going to talk about the traditional method. So the one question when I was studying, looking into RL, I know a lot of people have a different opinion, like is RL really going to solve the problem, not going to solve the problem? So the perspective I have is things, we actually had a lot of infrastructure being built by the computer scientists. I think Google, DeepMind, they're putting a lot of, like NVIDIA, putting a lot of resources to improving the computation to solve those kind of RL structure problems. So can I actually just think about, I'm going to use in those RL framework as a computational method, come back to my control problem, and how can I do use it? Even to start with a model base, I'm just using it as a computation method because there's so many GPUs, so many different solvers, and still that is so easy to actually learn to get started. That's kind of one question. Can I use that to do it? I also want to say, like the project that I just started with 3 years ago when I was doing my sabbatical at Google Brain. So my team, they're expert in reinforcement learning, and I was questioning them, like, what exactly are you guys working on? Like the problem I try to use on my problem looks like it's so hard to train. So we had a lot of conversation, and then eventually, like, I think they actually also care about physical system. Glad my team actually care about physical system. So like the work I've been present today is actually come from the collaboration since that conversation. Now, I'm going to talk about 3 parts. I will tell you what the representation really means. So first, I will just focus on, I'm going to use as a model-based, just computational approach. But there's no learning, the first part. And then I will go ahead, since I'm actually using the RL as the building core to build my algorithm, so it's easy be adapted to the data-driven scenario. And last one is the most recent work. We have been always questioned by when I present the work, how are you going to handle large-scale systems? So recently, we have able to extend the representation to large-scale network. Now, let me dive into the first one. So what exact representation do I mean at the connection between RL? To do that, let me give a very quick review of the MDP and RL, the language that I've been using. So we had the stage, like the time, similar to our time, state, action, they're almost the same as the nonlinear control problem we're talking about. This is one kind of slight difference way to represent the dynamical system. This is state transition, putting a probability, like derives a way to capturing the stochastic among the state transition. So state reward, same thing as before, policy, same thing as before, and the objective, similarly. So it's trying to maximize the runtime reward. So it's trying to the learner, the agent, interact with the environment. So now, let me say a quick overview of the reinforcement learning algorithms. So there are so many different kind of toolbox, but in my opinion, I always view them as this kind of interaction, depending on how you're going to interact with the actor and the critic. So what the actor trying to do? So actor actually means the control policy. Try to pick some policy class, parameterize it with a deep neural network. What kind of neural network to represent, depending on the person or the lag. And then trying to do the policy gradient. The policy gradient definitely hard to compute because you can imagine putting control policy, you want to do the long-term reward. So that kind of famous policy gradient theorem. So we can connect the long-term reward, which is the Q function, with the policy gradient evaluation. So you don't need to remember the details of the equation. The thing I want to highlight is the bottom line of this algorithm is trying to find a way to evaluate the Q function, which is an expected long-term reward. And the kind of summation of those R and a lot of computation will come for the next slides. And similarly, if we're trying to talk with a general nonlinear system, continuous state, continuous action, we need to figure out how to really represent the cost to go. It's not big table, it's not Q table, it's Q function. So again, represented by the deep neural net. The frustration, and there's an interaction between the actor critic. You can have a different loop, have a different time scale. The frustration always comes from what's really the representation, or what exactly the parameterization of the deep neural net I should start with. So I was trying to play with those PyTorch by myself, TensorFlow, and this is if I kind of adopt exactly what the people have been doing, fully exact the code, we'll probably still have some issue because there's some configuration of the pattern are different. And if I go beyond that, change my dynamical system, doing the similar neural net, regardless of chain, probably I'm not able to get the result. So a lot of frustrations about where to start. I guess almost everyone heard about the transformer. The big success for large language model, people figure out one good representation for those large language model, go ahead with the transformer structure. But for the control problem, what's really the representation we should use? So that's kind of start with the collaboration between me and the Google team is, can we kind of figure out the representation for the control dynamical system problem? I figure out some systematical and relatively simple way that people can just follow the process, and then using the reinforcement learning computation tool to proceed. So today my talk is going to focus on the representation for the Q function. So what's really kind of a natural representation I can use for the Q rather than to just treating as a black box, queuing back and forth. So this is probably the most important slide, the key idea. So where did the key idea come from? I said all those our algorithms kind of narrow down to do the evaluation. This is doing the Q function evaluation. The Q function evaluation is a long-term expected reward. You can do the recursive way. I put in the infinite time horizon discounted. That's the recursive representation of the Q function. So now let's look at one assumption. So if now a car, this is a state transition dynamics, which is the SA to the next state S, can be written down as the inner product of the two feature function. One feature function is the phi SA, the other one is US prime. Don't ask where that come from. That will be next slide. Let's say it has this very nice linear structure. What's going to happen? What's going to happen is this. Now my Q function, I'm putting that in the product, the linear form, into my Bellman equation recursion to compute the Q function. I'm putting the feature function phi SA one side, everything else is integration is fine. They becoming just like one parameter. The bottom line I want to say is this. If my state transition stay in the feature space represented by the feature function phi SA, then my Q function is linear with respect to this feature space. So why this is actually will be nice, as I mentioned earlier, mostly we try to find a function class to approximate the Q function. What this says is the function class we can stick with is just in the phi SA feature space. And then to learn the Q, just to do the least square to find the W. We're not going to do the integration. To find the W, go ahead using the RL, data-driven, this kind of method to find it. So indeed, this was actually like, you see the paper I put in here, 2019, even before that. Like people look into the structure, start with the assumption, and a lot of sample efficient RL algorithm. This actually can also apply to the continuous control, continuous action. Then the dependency will be only on the dimension of the feature space. So this is the key, but then when I started looking at those papers, I'm very confused. Right? What is the problem they try to solve? So those papers are very theoretical papers. They don't really to worry about physical system, and even don't have a simulation in the paper. Like, where does this really come from? Surprisingly, let me take a detour. Beginning, I was very hesitating, like, should I really go with that kind of problem? Like, start with this assumption, and where it's come from? So now take a side detour. So from the function rule analysis, like this is a function, has a 2 input. This comes similar to the positive definite matrix, but this is in the general function space, continuous space. We have a positive definite kernel. The Gaussian kernel is actually one of the example. No matter what really the ST is positive. Why talk about it? Now, because I want to find an inner product decomposition for my state transition. For this kind of positive definite kernel, and from the Bonnard's theorem, it's naturally I can put in a kxx prime into the decomposition of the feature function. And the feature function which actually we are actually familiar, it's actually from the Fourier, it's sine cosine, this kind of basis function with omega. So what's the use of it? Now back to our nonlinear control problem. So this is the dynamics we have. Let me put in the assumption, say this is Gaussian noise. I build in connection to the state transition language. It actually means the state transition is a Gaussian kernel. What it says, using the Bloch's theorem I talked about before, I can do the decomposition of the state transition dynamics. The state transition dynamics, look at here, this is a phi SA. This is a US prime. So you want, like from the community, people say it's called a linear MDP. So linear MDP is linear with respect to the feature space phi SA. But the phi SA, look at here, is nonlinear. It's encode our nonlinear function FSA. It has a sine cosine, the basis function. But the bottom line is we actually got a linear decomposition of the nonlinear dynamics. And then I put it here as a Gaussian assumption. It can be generalized to some other different noise, as long as you can represent as a positive kernel. For me, I felt like this is exciting. Okay, looks like this actually can capture almost all the nonlinear dynamic system. Great news. But back to the big picture, the question I want to have, I want to use this thing as a computational tool to find the control policy. So now let's dive into the computation. The immediate challenge is this. This is a very nice mathematical decomposition theorem. And from those Fourier transform idea you look at there, it's infinite features. The expectation and the rho omega, this is standard norm distribution. So it's at infinite dimensional, like what to do next. Natural way you would think about is I can do the truncation. Like similar to when we're using the Fourier series to approximate function, you're going to truncate. And in actually a different way, since this decomposition is on this random variable rho, we actually can do 2 different kinds of truncation. First is just the random, like don't really even think too hard. Just I represent in this decomposition the feature I'm going to pick, just ID sample features according to the standard norm distribution. By that, then we got a Q function. We know the feature space can be approximated by this finite series, the VSA. This is the one about random truncation. If we want a fancier way, like, oh, I want to do a better approximation, the better approximation we can do, then we can, this is similar to the singular value decomposition, pick the top features. So from the Mercer theorem, for the general positive function, we can decompose into the important feature to the less important features. And similarly, we just pick a truncation and to approximate it. I want actually feel free to ask questions, even this is a keynote speech, because I want to make sure everyone understands the key idea. This is the main thing. So now back to our algorithm. I'm not really need to design a kind of new thing. The only thing I kind of figure out is what's really the function approximation I should do for the Q function. There are many other papers when you open it, people making assumptions. Oh, there's a powerful function class that can approximate no matter what kind of Q function within epsilon accuracy. Where does that come from? There's such a one way. So I can, using my Fourier series as a feature function, which is encode the FSA, to do that. And then you can take whatever IO algorithm, pick your favorite toolbox, represent your Q function into this form, go ahead. Indeed, once we try, figure out this one, even for myself and my student who doesn't really have those kind of CS learning background, more theoretical, we go ahead to implement this representation by ourselves. And we start with inverted pendulum and compare with some other tools we have been doing from the control community as the iterated LQR with the Koopman operator, trying to swap the arms from the downright position to the upright position. So we also put into the application to the quadrotor, because later on I have some video to show about implement the algorithm on the real quadrotor, and to see how it's going to perform. We also try to see how the performance being improved if I increase the number of features. And the number of features corresponding to the unknown parameters. I want to compare with the petal-tensor flow toolbox we got. This is a much less parameters. They're always, the minimal number from those kind of toolbox always going to have 550K parameters, even for the small problem inverted pendulum. And for this one, even for the 4,000, it's able to do it. And of them from the random feature. And we were challenged last year when this work actually presented last year by some control professors saying, oh, there's a pendulum bot, which is the double pendulum. In the 1990s, there was a competition in the control community. People actually tried hard to see what's really the nonlinear control we can have. And you can look at energy-based methods from those papers. Indeed, the energy-based method has a very good performance for those nonlinear systems because it's really using a lot of knowledge of the physics. And we are glad our performance is actually can do better, even from those energy-based methods, people all had been optimized. So with that, you may wonder, do we have a theoretical guarantee? I'm not going to present in today's talk. So in the paper, we actually go ahead to analyzing the approximation error. As I mentioned, when I really do the Q function evaluation, it's not through the integration, it's not computational. We did the data-driven, find a sample, you have a Q function, treat it as a simulator, and you can use it as a generative model to approximate your Q function. And then we had a policy iteration, do those policy gradient, what's really the optimality gap. If you're interested, feel free to check the paper. So we also had, since I had those physics in my mind, I want to care about robustness. We can add robustness, and the robustness is going to be perturbation on the representation. We also have a safety set. And safety set, you can have a different type of safety set. We put in some safety set based on the state occupancy. This is basically means the frequency of the distribution on the state. And you can put in a constraint on that. If there's something you don't want to visit, you can put in that distribution requirement to be in 0. So why I put in this constraint? I'm not going to dive details, but want to highlight the Q function interpretation really heavily used the feature space VSA. So the original linear decomposition, when you recall it, it has actually two features. One is a VSA, the other is actually mu S prime. For the state transition, very interestingly, if I want to care about state occupancy, it will sit in the feature from the P decomposition, another feature space. What it says, if I go ahead to doing the data-driven method to solve this safety control problem, I will try to using this feature, function approximation, to approximate my state occupancy and to decide the algorithm. So this one's still ongoing work. This is just some preliminary results, the simulation we did for the safety one. So we try to put in this is even a Panzhong one, put in certain region, called that the safe region. And the control actually able to try to find out control policies, stay kind of using the minimal effort to stay in the safe region. And this is about the robustness. We did a perturbation on our feature space on both sides, VSA, mu S prime, and design our algorithm. And look at this. This is the non-robust. Like this is kind of cost by translated to the expected reward, negative one. So the higher the better. So this is a robust version. So we actually can do better once I add robustness into my perturbation. So with that, close the first part of the talk. I'm trying to making sure I'm in time. Good. So now I'm going to give you some idea about, like I said, this is I have a model. I treated my model as a generative model to generating all those samples. What if I don't have? Like I just have a system like I can probably play with to get in the data. So once we don't have the model, right, the one straightforward idea, kind of based on the system identification, from the data to build a nonlinear model, which you can use the system identification tool that people have been built. And then once I have the F, using the Banach theorem to get in the random feature and proceed getting the policy pi. But let's revisit here. So what's really things I'm using? It's not really the FSA. But what I kind of used is directly on the state transition probability. So another idea is how about just go ahead based on the data to learn the feature directly. And that is one question while looking at that is now just purely from the data, and now I want to learn a probability transition in this kind of feature space. What kind of method I'm going to do? So first, if I just look at, view those as the single value decomposition, finding a function approximation. This first, okay, let me just put the loss function to minimize. This is from the data representation. This is my feature space representation, try to find the feature representation to minimize the error. You can play with different norm. And then like I can really view those ideas as the single value decomposition. This is in the distribution space. What does this look like? But another more interesting thing, which is actually recent months, because I've been really want to understand this kind of representation better and better. Then look at this one. So this is actually what really the state transition dynamics is in terms of the probability language. It's a conditional probability distribution. Conditional on the SA with the probability of S prime. Now, once we view as a probability distribution, I don't know how many of you have been working on generative AI, generative model here. One building this connection is, now if I view, just focus on what I really learned is a conditional probability. What does it mean? I can using the statistical learning tools, and because of generative AI, people have been developing so many different tools. First, I think the MOE is not really computationally efficient, but this is getting like first start. Try to do the maximum likelihood, find a probability distribution. But then more interesting, which from our empirical test recently, is the contrastive learning is actually better performance. There are different formulations of contrastive learning depending what computation things you have. So what is being doing contrastive learning, in case you haven't really heard about it, is you go ahead, you also generate data from a noise distribution, like from a distribution, not from distribution you care about. And you try to find a model to describe, like making them be more different. So that's what we've been doing. This comes from the noise model. This is from this data is come from my true conditional probability. The different way to do it, some will have more computational power. And then once I connect with that, I can also do the score matching. Once I connect with score matching, what this means is you actually can also apply even the diffusion models, generative AI. So this is really the recent work we have been trying to, at the end of this year, hopefully my group will having one note to summarizing those different methods and at least report our own empirical performance. So far, I think this contrastive learning from our own simulation has a better performance. My collaborator actually say diffusion model is better. So like, it's still ongoing. If it's interesting, have talk more. But I want to spend a little even more time, right? So our community has been focused on a lot of them on the state space representation. You have the ST plus 1 equal FST AT. which is a great representation. And I can also connect with this kind of transition probability. And on the other hand, if I just kind of view whatever been going on with the generative AI, there are a lot of computations as a tool to actually build a dynamic, like a random model. And our stochastic control is a random model anyway, right? So I don't have an answer for that. It just, is there any kind of advantages if I view, just kind of really look at my system in the distribution space? So we have been also working on some other computation tool to really just capturing the distribution of the state to see whether we can have different, like other advantages. With that, let me come back. So I've talked about two different ideas. I wouldn't say which one is better. Just the second one looks as there are more methods to do it. But there's always one difficult challenge, exploration. So when we have it, we don't have the model, the data is only going to be limited, regardless. So we always need to do some exploration. So this simulated idea is just once you can do the sample and sampling, right? Just putting a bigger class. Each time you're going to random sample F, proceed the control procedure I talked about before. Or the other one, more like the binding literature and IO literature, I can also kind of add in some bonus function based on the uncertainty of my knowledge of my dynamics, adding this bonus function to encourage exploration. So we have some papers like talk about the way we've been doing, but it's still, like if you ask me, I don't know which one is better, which one is worse, and how you're going to choose the bonus function, the different tricks you're going to play, but once the expression wants to have both uncertainty from the feature space, which one is, like there's a lot of open questions in that area. So we simulated first the simulator, report the performance, like every time when you see people present the result, okay, our algorithm is doing the better performance. So I'm not going to spend too much time on this simulation because the most thing, that's why I'm looking at the representation. I want to really translate those computation or those control policy to some real physical system. So I started building my own research, like the robotics lab is from my own robotics lab. Like trying to eventually, like first we did a simulation on the quadrotor I showed you before, and gradually to see whether we can really implement on the drone. Like this is probably the simplest task to get started with. So then the one immediately like challenge what we're talking about, the representation we're talking about is to represent the state transition. If I have a simulator, right, the simulator has some state transition, but the real system is never going to be the same transition. So from my representation view, that is one of the bottleneck when I just translate control policy, learn from that tool. And then there's an advantage of the linear representation. What do I mean? Let me look at here. So let's look at the gap. So recap, let's say I have a simulator. From the simulator, I can treat this as a general model. I got the feature, the original feature called phi node, mu node. And I know my Q function, if I change the IO policy, my Q function will sit in this phi node space, which is great. But now, because the P is different from the P node, I know it's different. The good thing to put it into the linear feature space, this is the additional gap. You further continue to find the feature space. All the feature space is actually linearly dependent on it. What does this mean? Then what I can do is I can try to figure out a way using the knowledge we have about linear space to maximize the use of simulator or existing old data and figure out what street exploration I should do. Putting here what this means. From the function space viewpoint, this is a true P, and this is what I learned so far, this is the gap. So this one was represented, like spanned by the feature space I learned originally. It's not enough. Then I try to add more feature. So if you recall the linear operator class that have been taken, right? This is the procedure I've been learned. We start with some bases. If not enough, go ahead add another basis. If I want another basis to have a more representation power, I can put in this. This is orthogonal requirement. But if information already captured by my previous feature space, don't need to repeat it. So just add a new feature, which is orthogonal to the existing feature. And since the feature I was talking about is the sine, cosine, you actually know how to make this orthogonal condition be satisfied. And we implement this into the crazy fly in the lab. Let me go through the entire procedure if I use this representation. Is first, I have a physical simulator, learn the feature space. And when I have a simulator, I can also actually learn some initial control policy. So putting this into control policy, I will take into the real physical system. As you will see the video later, it's not going to work. So, but I will get some data. It's not going to work, but it's not really that bad. I get in the data, I will go ahead to update my feature, and then to retrain my Q function. I just gradually building up upon my previous knowledge. So, and then you just keep putting your RL algorithm in the loop. Now, let me show you the simulation. Hope it's. So we tested on the crazy fly. The good thing for the crazy fly, because control community, research community have been using this for many different research. Indeed, people have simulator already. So use the simulator building by other labs. And that's the initially, you just translate the policy, it's not going to work. This one, we actually we using the feature we learned, and then retrain the Q function and policy. You see, do better, but we didn't update the feature of state transition. Now, then we repeat the process by multiple rounds. So this is the final control policy we have. Once it's final, not really that final, we just kind of did 10-step iteration to cut in the data and update the policy. We sent this paper to, and this is from here, you can immediately see the difference. So this is the inventory, the control policy, almost straight line, going to the hub. So we sent the paper to IROS, and the reviewer were interested in this semester and also asking us, so that's why this is actually last week, we did the simulation. So let me first show you this one first. We try to change the environment. To add in. Now this approach is not that bad. The initial one you can see is being blown away, and then the control is coming back. We did a 3 round of iteration because the dynamics being changed with the wind. We did 3 rounds. Achieve better performance. And then I was asking the student, make sure now we train this controller is not for the wind environment, but then it will not going to work without the wind. So we try to change the wind, change the fan speed. And then so this video was obtained last week, and you can see for the fan, my student had to kind of find whatever available in the lab, and we found an old fan left by the old member from the furniture, and it's very manually. So hopefully, we are purchasing a more powerful fan, blow stronger wind, you will see more difference. So as you can see, the big, huge advantage, in my opinion, about the representation, it will give us a systematical way to figure out the gap. And the representation can take use of the knowledge as we learn from the simulator, or the knowledge we learn from original physical dynamics, or the knowledge from the previous data. You're just building upon it. Now, how many time I have? We'll check. Okay, good. So I will just very quick talk about how we're going to extend this to a large-scale system. For a large-scale system, go quick, is we have now individual agent, state, action, and it's a network. So it means the state will depending on the neighboring state. State reward, control policy, control objective. Everything's the same, except now I have larger dimension of the state and control action. So those kind of network local connectivity come from real application, like for the thermodynamics, the temperature of one room depending on the agency, rooms, congestion of a road depending on the nearby roads. That's where dynamics come from. But then the dynamics is always highly complex. We don't know how this kind of nonlinear really transfer to it. So first challenge is about control the actor, control policy parameterization. First of all, if I think about the global policy, it's not practical to use. So, and also this actually, if you're doing the global policy, the representation feature space will grow exponentially difficult once the dimension increase. So we have to do those kind of local policies. By local policy, taking from the local state to the local action. But first question, we know our community have been working on distributed control for a long time, how to find it. But one question is, how is that optimality that we really sacrifice? If I have the communication infrastructure, if I increase it, can I have a better performance? So we had a recent work, which is my student Ruyi, who is also in this conference. So we first flash, is this for the linear quadratic control problem? We found some condition and show that the optimal controller has a spatial decaying structure. It means actually even for the optimal global policy, I don't need much information about neighboring. The dependency is very weak. Based on it, what it shows is global optimal control K will close to the local structure. And what this means is that we have a performance guarantee about the local controller. So if I have a K-hop neighbor, and we can show the performance compared with optimal global policy, which is never going to be implemented in practice, it's decaying exponentially with the increasing size of the neighborhood. So which is great news. And then back to the learning question. Now, I know I'm going to learn the local policies, but how exactly to find the local policies, especially if my problem is nonlinear, is unknown. And back to the RL framework, I said the bottom line is finding the parameterization of the Q function. For the network case, what does the Q function look like? So individual agents have a local policy based on the local information, global policy parameter. And I can look at the Q function of the global system because my R is summation of individual reward. I put it here. I can have things called the individual Q function. But because everything is connected through dynamics, when you want the long-term reward, it's still depending on the global state, global control action. And again, that's like for this, if you really think about for the feature representation, once I have higher dimension, if I even one dimension need two feature, once you increase dimension, it's grow exponentially fast. That's how many features need. It's not computational. So how are we going to do it? So for the problem, for the network, because we start with the network problem, we look at this, how individual agent going to evaluate their cost to go. Practically, you can imagine, if I'm a person there, I'm not going to really take care of the entire system. But just look at my neighbors, using my neighbors' information to evaluate how good the control policy is. And I put in a very simple idea called truncation. But truncation means ignore the agent who is far away, and you can decide how, the large of the K-hop neighbor, how many agents you want to ignore. So nicely, for the network problem, we're able to show the Q function itself, it has this spatial decaying property. Indeed, the agent who is far away is not affecting myself much, and we're capturing the decaying rate. And what it says is we can just do the truncated local Q function. Back to the representation I talked about. Then I know that, but then how to represent the local Q? I had the representation of my global system. That's why not going to work. It's going to grow exponentially fast. So now let's look at how, for the network representation, what we're able to do is, now this is the transition dynamics, neighbors affecting myself. I'll represent in the probability, conditional probability language. And finding a feature, for individual one, I can have one feature space based on my neighbor information. The Q function, what we're able to show is it's going to be the corner product of the feature space from individual features. And you can decide how many hop of neighbor you're going to have. And we are able to prove the feature, the truncated, for the truncated Q function, it can represent by, we call it local features for my local neighbors. If I put in a summary, for the network case, we kind of talk about two representations. First is representation for the control policy actor. Second, and you can decide, putting the K kappa pi, you can decide how many neighbors you want to have. And to evaluate the policy, we can have a local critic of the local feature space. Again, you can decide how many hop of neighbor you're going to have. You can be different. You can even be lazier, putting a smaller neighborhood to do it. And doing the iteration between the intersections. Now, putting the example, this is the thermodynamics. We pick 50 agent here. And look at this. This is the optimal K. And this is exponential decaying. Look at if the K-hop neighbor getting larger, this is the value, this is the log scale. And then we actually test the learning algorithm on it. So this is our learning algorithm. It's very interesting for this one. You look at the gradient step, it's only need 40 gradient step. We kind of almost learn the optimal local controller. So this is about just don't use any neighbors information, just myself. But we did, for the Q evaluation, we probably did a one hop neighbor, and this increased the neighbors information. Look at the red one, it's almost close to the optimal global performance. So putting in summary, I almost close my talk. 1 minute. So I talk about representation. Everything starts with this kind of linear decomposition, but it's not really linear. For the data-driven, talk about the advantages, how this then can build on the previous simulated, previous knowledge. And for the network case, we can talk about the actor, critic. There's many, many ongoing future work. Like, what about actor representation? If we really have a very large, like the PDE model. So what is the fundamental trade-off between the exploration, exploitation, on this representation? And always, I think for us, we care about, like, can I have a formal guarantee of the stability? I will guarantee about optimality, but optimality in terms with respect to what? If the system is unstable, even you say optimal, it's not really ensure the stability of the system. There are many things beyond the local structure. So close the talk is, there are many other challenges. I don't have time to talk, and also I don't have an answer to close all those challenges. Like, what if your data is really small, time-varying environment, when you don't have a simulator, don't have any preliminary data to start. So for that, I would say, actually come from the domain knowledge, really go out to build. So with that, I want to close my talk. You want to have a few slides talk about application. Well, I prefer to speak offline. If you're working on those simple applications, happy to talk offline. So thank you, everyone.
Thank you, Lina, for the stimulating talk. Any questions from the audience? Maybe a microphone? Yeah, just. Yeah. Push it upwards.
There's a button down the bottom that's.
Can I try?
Maybe this is it.
Yeah. It will blink green.
Yeah.
Yeah.
Okay. Fantastic. Maybe ask you two philosophical questions. Maybe let's just ask one because maybe others want to ask questions. How do you think one can reconcile reinforcement learning with safety guarantees? You know, you certainly showed that crazy fly, but you know, any learning scheme that's based on an optimization criterion, I don't think can be guaranteed to meet the kinds of safety guarantees. So what do you think philosophically is how you bridge that gap?
Yeah, okay, great question. And I'm glad you said the philosophical question. I agree. So first, I think for the safety, first of all, I think the safety definition is very broad. For different application, and they have different kind of the safety criterion. And in fact, if I take in the crazy fly, like even this one, I didn't really guarantee the real safety, right? The next level, we want to put in to the crazy fly, flying in this room, had obstacles, that one we haven't really tried yet. So for the algorithm, and then regarding that, right, then how much safety we can really achieve? Can I really guarantee 100% regardless environment? I don't think I'm able to do it. And I even don't think even you put in any kind of, like even for the control method, you always have some corner case, you're not going to guarantee safe. So more interesting for me, that will be like, can I really provide a certification, right? I can put in some conditions. I know this kind of conditions, I can guarantee those treatment. And since I translate everything into those kind of probability random process, right? Ideally, the way I want to do it, probably it's provide high probability guarantee, like 99.9, but it's not going to be 100%. So that's kind of my view, if I further push in the safety guarantee. But then another, like even safety guarantee also like about stability. I think that one is like, if I don't have anything else, at least I want to guarantee stability. That's something I really wish like for the next step to making that be more like 100% under like the typical environment. I'm not sure whether this answers your question.
One more. We can do one more and then we take the rest offline, I think.
Or should I let you wait for the other?
I think go ahead so that we have a closer to the topic.
Oh, okay. So, you know, just about that sim to real, of course, you know, the most engaging problem of our times because nobody in industry dares to use AI methods without really bridging that sim to real gap. But do you think that adding extra features is the way to get better, to reduce that sim to real gap? I mean, there's a point of view, I forgot her name in Georgia Tech, she has extensive experience to show that it's better to do learning on low-fi sim models and then apply the learning on low-fi models to high-fi models. And that's consistent with what we do in control. You know, if it's walking, you do a inverted pendulum model or something like that, and then you sort of work your way up. But it seemed to me that your approach was to add extra fees when you felt that the sim-to-real gap was too large. So what's your take on that?
Good question. I do think even this one is kind of connected to the approach you were talking about. Right? Start with a kind of low fidelity model, high fidelity model. This is even the way is like, I think the boundary for the low fidelity model, even calling about the feature representation, will be actually easier to learn first round of features, and then go with high fidelity, taking more time to improve your feature. So the feature representation, in my opinion, is actually very broad. I was talking about the VSA. So there's some people who has more computer vision in the lab with the robotics. So the nice thing for this kind of thing, the VSA, you actually can also encode the feature from your computer vision features. And that's even a bigger question. I mean, how much we really like want the computer vision, how many features it will have to really making sure it can fly under different environment. I don't have an answer for that. But the good thing, in my opinion, for this approach, it's provide a systematical way to even connect with the tools built in by other community. And then I also have a way to gradually improve it. And but then it's not really like if like here I'm talking about from the random feature, right? People can also go with some other way to represent it.
Okay, let's thank Lina once again for the excellent talk.
Thank you.